I first met Bill Hahn at the research lab in 1937. He had come from the Chicago district where he was an engineering consultant, I believe. I'm not sure about his early history at the Chicago office. But when I arrived at the lab, Bill Hahn, was having problems with relation to experimental setups for his Klystron experiments. And I worked with him to see if we could get some circuitry that would function with his demountable vacuum system. This led to our making a tube which in effect was a container for an electron beam, which then could be used in experiments to determine the kind of circuitry that you could hang around the beam and influence the beam that way. I spent some time working out the problems, primarily high RF fields that would melt the envelope. And we ended up with quartz envelopes, which that gave us some trouble with losses, that is, high frequency losses in the glass. And that's about all I can contribute at this time on that subject.
Well, now there's been a break of World War II. Much of the activity during the war on tubes of these power classes were in magnetrons, and the Klystron work that Hahn had been doing didn't materialize as a usable power source for a number of basically technology reasons, namely realizing the hardware. So we move on to a period of time following World War II when UHF television was begun, and the need was for a transmitter for higher power than could be obtained from tetra-type space charge control tubes. The Varians had been working on the Klystron, as is known from much history, but hadn't been able to put their early models through to a production phase. So GE supported Varian to build a tube 15 kilowatts of sync peak power for the UHF television band, and that was 48-49 time frame. The research laboratory of GE was not involved in that particular effort. It was a product department effort between General Electric's tube department and Varian. But about 1949, a need arose for a high-power radar transmitter, a system called FPS-7, which was an Air Force long-range search radar, where the power requirements were 10 megawatts of peak power and something in the order of 15 to 20 kilowatts of average power. And the magnetron tube that they were using or trying to use didn't work. It was unreliable, and production couldn't do it. So W.R.G. Baker, who was managing the electronics sector of the company at the time, came to the research laboratory to Dr. Suits and said, I need this high-power amplifier. He knew of the work that had been started at Stanford University for a linear accelerator by Dr. Chodorow and Ginston, and a project was set up between the Syracuse people who built radar systems and ourselves at the laboratory to develop a tube, which we numbered the L128. That just happened to be a laboratory type designation. So we began work on that by essentially consulting with the people at Stanford on what they had done, and then moved on from there pretty much by empirical means to realize this tube, which was to be at what we call L band, namely 1.2 gigahertz more or less, and tunable over a relatively, for that time, wide range, namely 150 megahertz, and the power output of 10 megawatts, power gain of at least 30 dB, and an average power of 17 kilowatts. So what we have here is one of those L128 Klystrons, and I'd like to describe basically how it was made and some of the design problems that we encountered. What a klystron is, basically, is an electron beam traversing a very large distance down what we call a drift tube to an electrode up here, the collector. Now down at the bottom end is where everything starts, which is called the electron gun. It's way down at the bottom. You'll see a white ceramic insulator. That houses a hot cathode and some focusing electrodes, and the entire accelerating voltage for the electrons appears across that one insulator, in this case 230,000 volts. That very high voltage beam, now an electrostatic beam, is put through what we call a magnetic pole piece, an iron plate, and goes down a long drift tube and stays collimated by means of a large electromagnet, which is not shown here, it's been removed, that keeps the beam from spreading. And as it goes down the drift tube, it traverses some microwave resonant cavities. Here's the first one, the second one, and a third one, which is this complicated structure here. In the first one, the electrons, which normally have the same velocity, all of them, have their velocities modulated by the RF, so that over time there are some fast ones and some slow ones, which as they drift to the center cavity end up in bunches. Electrons faster than the average catch up with earlier ones and so forth. This middle resonator, which is not connected to any external drive system, remodulates the beam in a more intense fashion to further enhance this bunching so that electrons end up clumped in time, spaced one cycle time apart. And that is a necessary requirement to generate energy by having those electrons give up energy to an electric field, RF electric field, in an output gap, which is here. And the power is coupled out because of its high level via a waveguide. And one of the real development problems was to get the power to come out to air, or in our case, a gas-filled, high-pressure gas-filled waveguide in a vacuum seal. And this is called the microwave window, which has some requirements on it that it be transparent to the microwave, be a good vacuum seal, and sustain a very high voltage all the time. That was another significant development problem we had with multipacting and other esoteric failure modes, which were solved over some long period of time. I should say that this project I'm talking about began about 1950 and took 5 years to consummate in developing tubes that were deliverable for system use. Now, the electron beam does not convert entirely to microwave energy. There is waste energy. Roughly 35% of the beam energy comes out as microwave energy. The other 65% is dissipated in an electrode up here called the collector, and it is water-cooled and involves a fairly careful thermal design to avoid melting the parts, because the electron beam, as it comes into this structure, doesn't spread uniformly over the whole surface area. Some of it is concentrated, and we had to worry a lot about the thermal aspects of it. But with a large amount of empirical design obtained over these 3 years or 4 years of effort, a tube was finally developed, which was the highest power radar tube at the time, and the system was successful.